those two pulleys is the belt. Okay? And the belt is moving at a linear speed. That belt, suddenly as it's going around this pulley, that belt does not all of a sudden speed up around the small one or slow way down. That belt is moving at a constant rate all the way that it's connected to. Okay? Because it can't go faster on one end than it can on the other. Okay? So with that being said, we need to find the linear speed of that belt. Well, that belt is going around this big pulley right here, and that big pulley is spinning at 4 pi radians per second. So what we need to do is we need to say, well, this is 4 pi radians per second now, and that then has to be converted into inches per second. Well, 1 radian on the big pulley is 5 inches. So that tells me that the linear speed of the belt is 20 pi inches per second. That belt is spinning around at 20 pi inches per second. Okay? Now that belt is connected now to the little pulley. So the little pulley is spinning around at 20 pi inches per second. Because when we're connecting two pulleys, linear speed is what is connecting them. We can switch that then to angular speed by saying here now that the radius of the smaller pulley is 2 inches. So now I'm in radians per second. And that then would become, what's that, 10 pi radians per second? This would also work for typical problems that we would see on this one. So if we've got a saw blade and the motor is not attached to the drive shaft of the saw blade, usually it's attached by a belt. Okay? Bike. Okay? If you're pedaling on a bike, how much do you have to pedal to go a certain distance or to go a certain thing? Because they're all kinds of different. Okay? Alright? So let's try this one. You try this one now, I should say, would be a better way of me saying that. Okay? So a 4-inch diameter pulley on an electric motor is running at 1450 revolutions per minute, connected by a belt to a 9-inch diameter pulley on the saw arbor. Okay? That's the saw blade, is another way of saying that. Find the angular speed of each pulley and find the speed of the saw in revolutions per minute.
Not like, no, there's so much room. Just go home. So excited.
Okay, so 1450 revolutions per minute is what it is going, right? So we want radians per minute on that one. So I'm already in minutes. So 1 revolution is 2 pi radians. Want it to be in radians per minute. Fantastic. So the saw, or the motor, I should say, is spinning at, what's that, 2900? Pi radians per minute. Would you agree with that? Okay. So the saw now, okay, so the motor is spinning around. It's connected by a belt. Okay, it's connected by a belt, so we got to find the linear speed of that belt, which is finding the linear speed on either side of that belt. So I can take the motor spinning at 2900 pi radians per minute, and I can say, well, that motor has a 4-inch diameter pulley on it, which means then that 1 radian on that motor is 2 inches. So now I'm in inches per minute of the motor. That's the inches per minute of the saw. So then now I can switch that into, we had a 9-inch diameter saw. So that's 4.5 inches is now 1 radius on the saw. And I'm back to radians per minute. So, do some maths here. 2900 divided by 4.5. Yeah, that's not going to work. And then times 2. Yeah, that's not going to be a good fraction. All right, so what do we got on that one? So that's going to be, so this is 2/9 here. Yeah. So 2900. So I get, as an exact answer, I get 11,600 pi over 9. Okay. Find the speed of the saw in revolutions per minute. Well, I'm going to use my exact. What's up?
Can you explain this saw one?
What do you need to explain?
How did you?
So do you agree that the so on my diagram up there, the motor is the right one? Because it's got the smaller one, right? Okay, so this is my motor, this is my saw, right? What's connecting them? The belt. Okay? So I've got to connect them somehow. So I've got to, the only thing that's going to connect two spinning things that aren't the same size is the linear belt that connects them, or the linear chain, or whatever's connecting those two spinny things. I have to get that speed. Okay? All right? So that's linear speed because it's going a distance now to the other pulley, if you will. Okay? All right? So I need to get my motor is spinning at 2,900 pi radians per minute. We agreed with that, right? Okay? So I converted it first in green to inches per minute. That's a linear speed, right? Okay? So that's the linear speed of that belt going around between those two pulleys. Okay? What? I didn't use a 2-inch diameter, I used a 2-inch radius. Because it was a 4-inch diameter pulley on an electric motor.
So the pulley
is what's spinning.
So you use the motor radius?
Yep. To get the linear speed of the belt. Okay? Then that linear speed gets transferred over to the saw. Right? Which is the 9-inch diameter, so that's one radius is 4.5 inches. Okay? And then I did that math.
Like the test, are we going to need to do it the specific way? Because I'm kind of shortcutting and doing like 2,900 pi times 4 over 9 or other things like that. Or do you need it specifically to do it like order?
Depends on if you want to get partial credit for getting it, if you got it wrong. You know what I mean?
Yeah.
If you're 100% confident in it, you go. Okay? But if you're not 100% confident in it, then I want to see all of your math so that I can pick out where the mistake happened. Okay? Right? So now I'm in the... So do we agree then, Mad Dog, that this is our angular, or excuse me, the angular speed of the saw? Okay? All right? So now I need that in revolutions. Well, 1 revolution is 2 pi radians, correct? So my radians go away, and now I'm in revolutions per minute. Oops, I should have put 9 down here. This should still be a 9 there. No? Okay? So that's going to be 11,600 divided by 2 is going to be 5,800 over 9 revolutions per minute.
Does the pi just choose
That pi cancels out that pi. That's a Q. Okay? In the Hardy Boys adventure, while the clock ticked, the pendulum of a grandfather clock at the Purdy place is 44 inches long, and it swings through an arc of 6 degrees. Find the length of the arc the pendulum traces. Well, for those of you that don't know, in a grandfather clock, it looks kind of like this, and then it swings over to here. And if that swings over to there, then this is a 6-degree swing. We want to find the arc length, how far that pendulum swings. So what is that one? what should we use? S equals theta r. What's the problem with using S equals theta r? What do you got? We need it in radians. So theta's got to be in radians. Okay. So 6 degrees is that one. What do I multiply that by? Pi over 180. That's going to be my theta. Oops, that should be an equals there. What's my radius? 44. Coley, did you have a question? Or are you just going to give me the answer?
Yeah, I was just gonna
Okay. What'd you come up with?
Oh no, I was gonna tell you more, but
Oh, okay.
I can do it though.
Okay. So this is what? An exact form? 22 pi over 15. Yep, that's what I got. And that's in inches, correct? Yeah. Okay. In unexact form, what is 22 pi divided by 15? 4.608. Now, we posted this morning on the It's Learning, we posted some book homework problems for you. So you can definitely do those. And then we'll get more homework tomorrow. Okay? What's up? Sure.